Welcome back to Introduction to Higher Mathematics. In our last lecture, we explored the mysterious concept of infinity. We opened with a deeper look into the concept of cardinality, the size of a set. And we reinvestigated the idea that two sets have the same cardinality if and only if there's a bijection between them. We saw that infinite sets work in strange ways when it comes to cardinality, because one set can be a proper subset of the other, and yet actually have the same cardinality. So with that in mind, we defined the notion of a countable set, which could be finite or could be countably infinite. From there, we started with the natural numbers, our first countably infinite set, and showed by coming up with just the right bijections that the integers and even the rational numbers were actually countable sets. On the other hand, the real numbers turned out to be uncountable, as we showed by Cantor's diagonal method. Even if we try to list them out, with a clever rule, we can easily find at least one real number that hasn't been listed. Finally, we looked at the strange properties of arithmetic with infinity, as demonstrated by Hilbert's paradox of the Grand Hotel. The fact that the real numbers are somehow more numerous than the rationals surely seems strange, and takes a while to come to grips with. But once you get past that little hurdle, the real numbers often turn out to be the perfect number system in which to do math. They have just the right combination of useful properties. We're going to see some of those properties at the end of this lecture. In order to get to that point, though, we're going to need to go into a bit more detail into just what the real numbers are. Sure, we can describe the real numbers in terms of finite or infinite sequences of decimal numbers, but to really give them a firm foundation, we're going to need to buckle down and find a formal way to actually construct them. Actually, thinking about it, all of our subsets of the real numbers we talked about in Lecture 5, the natural numbers, the integers, the rational numbers, were described intuitively. So we're actually going to start at square one, literally, and build each of these sets from the ground up, starting from scratch. Let's start with the natural numbers. The natural numbers, in a way, are our most basic set of numbers. They're the numbers we use to describe all sorts of objects in the real world when we count them, hence the name. But how can we actually create the natural numbers? That's a question that was answered by Italian mathematician Giuseppe Peano. Peano laid out a set of 5 axioms that define the natural numbers. We'll be using our original definition of the natural numbers, the one in which the natural numbers begin with 1, not 0. In fact, this is how Peano himself actually defined the natural numbers. However, the same axioms can be used to define the natural numbers with 0, with only a couple of slight modifications. So the first of Peano's axioms was simple. There exists a natural number 1. The natural numbers need a place to start. And what better a place to start than 1, right? The second axiom introduced what Peano called a successor function that takes in a number and outputs the next number. So the second axiom says that if A is a natural number, then the successor of A is a natural number as well. The third axiom states that 1 is not the successor of any natural number. Now, if we were talking about the integers, it would be easy enough to say that 0 comes before 1. But we haven't defined the integers yet. So, Peano's third axiom firmly establishes that 1 is the root of all the natural numbers. The fourth axiom states that if two natural numbers have the same successor, then they must actually be the same number. That sound familiar? Think back to our lecture on functions. What the fourth axiom is basically saying is that our successor function is left unique, so it's injective. The fifth and final axiom states that if a set S contains 1 and contains the successor of every number in S, then S must contain all of the natural numbers. This may sound familiar to you. It sounds just like our typical argument for mathematical induction. So it should come as no surprise that this axiom is often known as the induction axiom. Well, there we have it. These 5 axioms don't just define the natural numbers, but in a way, they sort of create them. What we actually call this in mathematics is a construction of the natural numbers. In this case, we constructed the natural numbers merely out of a set of axioms. Now that we have the natural numbers at our disposal, though, we can add those to our tools in order to construct further sets. Let's do exactly that now and construct our next set in our hierarchy, the integers. Before we begin, think back to when you were in elementary school and were first learning to subtract, and were given a problem like this. You were told, you can't take 3 from 2, 2 is less than 3. Well, this is true if we want to stay in the natural numbers, because if we were to try to take 3 from 2, we'd end up with a negative number, -1. This actually gives us an idea of how to construct the integers. Keep that thought in the back of your head as we do this construction. What we're about to do may seem strange at first, but when you make the connection, it'll all make sense. What we'll do is we'll consider the set n squared, that is, the Cartesian product n times n. So the elements of this set are ordered pairs of natural numbers. Next, we can create an equivalence relation on these ordered pairs. Suppose we've got 2 ordered pairs, perhaps AB and CD. Then we can define an equivalence relation on these, saying that AB is equivalent to CD if A plus D is equal to C plus B. So for example, we might see that 2, 5 is equivalent to 8, 11, because 2 plus 11 and 5 plus 8 both equal 13. Try to verify on your own that this is in fact an equivalence relation. You should be able to show that it's reflexive, symmetric, and transitive. Now, since we've defined an equivalence relation, what have we partitioned n squared into? That's right, equivalence classes. Now here's where things get interesting. We're going to give a name to the equivalence classes. We're going to call them the integers. Confused? Think for a moment about what that ordered pair might represent, how you could translate it into an integer as you know it. I'll tell you the answer in a moment, but for now, let's continue to work with these strange ordered pairs in their abstract form. We can also define operations on this new set that we're calling integers. First of all, addition's pretty easy. We can just say that the equivalence class of AB plus the equivalence class of CD equals the equivalence class of A plus C, B plus D. So for instance, 1, 2 plus 4, 6 equals 5, 8. Now remember, we've done something like this before. We actually constructed the residue class mod m from the integers a couple of lectures ago. But remember that we also had to show that our operation is well defined. So let's go ahead and do that. Suppose that AB and A prime B prime are in the same equivalence class. And so are CD and C prime D prime. If we add AB and CD, we get A plus C, B plus D. But if we add A prime B prime and C prime D prime, we get A prime plus C prime, B prime plus D prime. So we need to show that these two equivalence classes are actually the same. So since A, B, and A prime B prime are in the same equivalence class, by our definition of the relation, we can conclude that A plus B prime is equal to A prime plus B. And similarly, C plus D prime equals C prime plus D. Now, adding our two equations together, we find that A plus B prime plus C plus D prime equals A prime plus B plus C prime plus D. Since addition of the natural numbers is commutative, we can switch the terms around in the middle and find that A plus C plus B prime plus D prime equals A prime plus C prime plus B plus D. Since addition of the natural numbers is also associative, we can also group the terms however we want. So let's put some parentheses in there. The sum of A and C plus the sum of B prime and D prime equals the sum of A prime and C prime plus the sum of B and D. But wait, this looks exactly like our equivalence criterion we've been using, but with the ordered pairs A plus C, B plus D, and A prime plus C prime, B prime plus D prime. So just as we wanted to show A plus C, B plus D is equivalent to A prime plus C prime, B prime plus D prime. So we can conclude that addition is well defined. We can also define multiplication on our new so-called integers, though the definition is tricky. We say that AB times CD is AD plus BC, AC plus BD. So for example, 3, 1 times 1, 3 equals 9 plus 1, 3 plus 3, which is 10, 6. Multiplication is well defined as well, though I'm not going to detail it here. Try to prove that one on your own. It's a bit trickier, but I'll give you a hint. Start off with the equivalence you'd like to prove, and try to work backwards. You're going to need to do some factoring to figure it out. Well, I suppose I've led you on for long enough, so now it's time for the big reveal. How the heck are these equivalence classes of ordered pairs supposed to represent integers? Well, let's look at our equivalence relation. AB is equivalent to CD if A plus D equals C plus B. With a little algebra, we would see that this is equivalent to A minus B equals C minus D. That's right. The ordered pair AB represents the integer A minus B. So for instance, the ordered pair 4, 1 would represent 3, whereas 1, 4 would represent negative 3. But there are many ways we could represent 3, not only 4, 1, but 5, 2, 6, 3, 18, 15, 1337, 1334. The possibilities are endless, which is why we use equivalence classes to compile all possibilities into one package. Try it out. You'll find that addition and multiplication of integers, using our definitions we just made, works exactly the same way as you're used to for integers. So why didn't we just say that AB represented A minus B in the first place? Well, remember what I said earlier. When dealing with the natural numbers, we would say, you can't take 3 from 2. So it wouldn't have made any sense to say A minus B. There's always the chance that B would be greater than A, and so A minus B would be complete nonsense. But while we can't always subtract natural numbers, we can always add natural numbers. So that's why we set up the equivalence relation in the way we did. By the way, 0 is of course represented as well in our ordered pairs. If A minus B equals 0, then A equals B. So all the ordered pairs where the two numbers are equal represent 0. Well, with the integers in our arsenal, we can construct another new number system, again using ordered pairs. See if you can figure out what we're constructing this time. This time, we'll be getting our ordered pairs from z times n. The first number in each pair is an integer, and the second is a natural number. Again, we're going to establish an equivalence relation on this set. This time, we're going to say that AB is equivalent to CD if A times D equals C times B. So for example, 2, 5 is equivalent to 10, 25, since 2 times 25 and 5 times 10 both equal 50. So, of course, our set is again partitioned into a number of disjoint equivalence classes. Furthermore, just like last time, we can define the operations of addition and multiplication on these equivalence classes. This time, when we add AB and CD, we get A times D plus C times B, B times D. So for example, 1, 2 plus 2, 6 equals 6 plus 4, 12, which is 10, 12. Multiplication is actually the easier one this time. We say that the product of AB and CD is A times C, B times D. So for example, 1, 2 times 2, 6 equals 2, 12. Again, you should try to prove that addition and multiplication defined in this way are well defined. The process is very similar to the last time. So what was the point of this new construction? Well, you've seen the set with these properties plenty of times before, but you usually don't write AB as an ordered pair. You usually write it A over B. That's right, we've just constructed the rational numbers. In fact, all you have to do is write all of the ordered pairs that we've been working with using fraction notation. And the familiar properties of adding and multiplying fractions are all right there in front of you. The rational numbers let us solve some equations that wouldn't have been solvable in the integers. For instance, recall how when we were talking about number theory, we said that the equation 3x equals 14 has no solution in the integers. But by extending our number system to include the rational numbers, our equation now has a solution, the rational number 14 over 3, or 4 2/3. But there are other equations that have no solution even in the rational numbers. For instance, the equation x squared equals 2 has no solution in the rational numbers, because there's no rational number that satisfies this equation, only rational numbers that get tantalizingly close. So how can we further extend our number system to be able to handle all of these cases? Well, we could choose to define such a number, calling it, say, the square root of 2, like we're already familiar with. Then we can add it to or multiply it by any rational number to have more numbers to work with. What we would have created would be an extension of the rational numbers, which we could write as q of square root of 2. Now there's a number of other equations that have solutions. But wait, what about x squared equals 3? Well, it looks like we have to take care of that one too, and extend q by the square root of 3 as well. As a nice bonus though, since square root of 2 times square root of 3 equals square root of 6, this takes care of the equation x squared equals 6 too. But what about other powers? What about the equation x cubed equals 3? Well, now we'd have to extend by that too, and add the cube root of 3 to our field, which would also include the cube root of 9. We shouldn't be restricted from multiplying the cube root of 3 by itself, so we need to include all powers of it as well. Anyway, you can see that this could go on for a while. But we could theoretically include all possible roots and combination of roots with each other and our existing rational numbers. What we then have is a set of what we call algebraic numbers. The algebraic numbers can be thought of as the set of all possible roots of non-zero polynomials that have only integer coefficients. The set of algebraic numbers is represented with a double-struck capital A. Technically, we haven't actually created all of A yet, because A contains the imaginary number I, because it's a solution to the equation of x squared plus 1 equals 0. So right now, we're only talking about those particular algebraic numbers that don't involve imaginary numbers. We say that this is the set of the real algebraic numbers, which we might write as A intersect R. Now that we've extended Q to include the real algebraic numbers, have we found the entirety of the real numbers? Not even close. How do we know? Well, as it turns out, the algebraic numbers, and therefore the real algebraic numbers, are actually countable as well. This may seem strange, but here's why. The algebraic numbers are the roots of all possible non-zero polynomials with integer coefficients. The integers, as we saw last lecture, are countable. Now remember that when we showed that the rationals were countable, we created a grid. In essence, we actually represented positive rational numbers as ordered pairs, the first of which is the numerator, and the second of which is the denominator, just like how we represented them in our construction earlier. It can be shown, though I'm omitting the details here, that if we're taking elements from a countable set, then not only is the set of all ordered pairs of such elements countable, but so is the set of all such ordered triples, ordered quadruples, and so on. In general, as long as n is finite, the set of all n tuples full of elements from a countable set is guaranteed to itself be countable. And when you think about it, it's easy enough to turn an nth degree polynomial into an n tuple. Simply pluck off the coefficients and throw them into the tuple. And you can go the other way as well. So the set of polynomials with integer coefficients is also countable. Finally, an nth degree polynomial can have at most n distinct roots. So every one of those polynomials has a finite, and therefore countable, set of roots. Again, I'm omitting the details here, but what it comes down to is that since a countable union of countable sets is itself countable, we can conclude that the algebraic numbers are countable, and therefore certainly the real algebraic numbers are countable as well. So why does this matter? Because the real numbers are uncountable. The set of real numbers is much larger than the set of real algebraic numbers. Numbers that are not algebraic are called transcendental numbers. You already know at least two transcendental numbers, the half-circle constant pi and Euler's constant of growth e. These are only two examples, though, which is part of what makes it so baffling that the vast majority of the real numbers are transcendental. We work with rational and algebraic numbers in our everyday lives and see transcendental numbers as these rare exotic exceptions, when in reality, they're only the tip of a much, much larger iceberg. So we're going to need to try a different approach if we want to try to construct the entirety of the real numbers. The approach that we'll take was conceptualized by German mathematician Richard Dedekind, who came up with this method of describing real numbers while he was teaching calculus for the first time at the Polytechnic, a university in Zurich. Imagine that you have a number line, but it only contains rational numbers. Dedekind noticed that he could cut the rational numbers at a particular number, and by doing so, partition the rationals into two non-empty sets. A lower set containing all the rational numbers that were strictly less than that number, and an upper set containing all the rational numbers that were greater than or equal to that number. This kind of partition of the rational numbers is nowadays known as a Dedekind cut. These Dedekind cuts are actually the key that lets us finally construct the real numbers. Suppose that we cut the rational numbers at 1/3, which is itself a rational number. Then the upper set of our Dedekind cut actually contains the number 1/3 at which we made our cut. So the lower set contains all the numbers that are less than 1/3, and our upper set contains all the numbers that are greater than 1/3 as well as 1/3 itself. But what if we make our cut at an irrational number? Perhaps we could make our cut such that the lower set contains all the negative numbers union the solution of the inequality x squared is less than or equal to 2 in the rational numbers. We've already said that there's no solution to the underlying equation x squared equals 2 in the rational numbers. So the solution x to that equation must be irrational. Whatever irrational number x happens to be, the lower set of our Dedekind cut contains all the rational numbers that are less than x. Then the upper set contains all the rational numbers that are greater than or equal to x. But there is no rational number who squares 2. So everything in the upper set is actually strictly greater than x. We've essentially found that there's a hole in the rationals where we made this cut. And this will happen with any irrational number that we can come up with. Making a Dedekind cut at that number will partition the rationals into those that are strictly less than that number and those that are strictly greater than that number. But this is a great thing, because now that we have a way to represent all the irrational numbers, we can just define a real number, rational or irrational, as a Dedekind cut of Q. We're not just taking it on faith that these irrational numbers exist, we actually are expressing them in terms of the rational numbers, which are already defined. What's more, we can actually define operations on these Dedekind cuts, and use them to define operations on the real numbers. To make things simpler, because of the way we define the lower set and upper set of a Dedekind cut, we can actually refer to such a cut entirely by its lower set, since the upper set is just the complement of the lower set in Q. With that out of the way, let's talk about addition. Suppose we have two real numbers, each of which is determined by a Dedekind cut. Let's say the lower sets of these cuts are A and B. So from this point, we'll refer to the cuts themselves as A and B. Then what would the sum of those two real numbers be? Remember that A and B are sets, so our answer should be a set as well. Any ideas? It turns out what we need to do to find the sum of those two real numbers is form the set of all possible sums of one element of A and one element of B. That is, A plus B is the set of all little a plus little b, where little a is in A and little b is in B. The idea is that since the elements of A will get incredibly close to the real number defined by A, but never reach it, and the elements of B will similarly approach the real number defined by B, by adding the elements of A and B, those sums will approach the sum of those two real numbers, yet never reach it. We can also define subtraction, multiplication, and division on these cuts, though we have to be careful when dealing with negative numbers. For instance, subtraction of A and B would be defined as all little a minus little b, where little a comes from A, but little b comes from Q minus B. In other words, the upper set. Because if we negate all the elements in B, the lower set and upper set will swap places. We need to make sure that the lower sets we obtain are always less than the real numbers we want to end up with, never greater than or equal to. Otherwise, our result isn't a Dedekind cut as we've defined it. So, with the real numbers now defined, it's time to start looking at some of the properties of those real numbers and see how they might be related to our construction that we've just done. First of all, the real numbers are ordered. In fact, they're totally ordered. And what's more, this order relation is trichotomous. We can compare any two real numbers, x and y, and find out that exactly one of three things is true. Either x is less than y is less than x, or x equals y. The Dedekind cuts give us exactly the tool we need to evaluate whether one real number is less than another. Since the lower set of a Dedekind cut contains all rational numbers that are less than some real number, if x is less than y, then everything in x's lower set should also be contained in y's lower set. But some elements of y's lower set won't be in x's lower set. So if the lower set of x's Dedekind cut is a proper subset of the lower set of y's Dedekind cut, then we can conclude that x is less than y. To talk about one more useful property of the real numbers, and perhaps one of the most important, we first need to define a few more concepts. Suppose we have a set A that's a subset of a totally ordered set S. If we can find an element of S that is greater than or equal to every element of A, then we call this an upper bound of A. So for example, consider the set of all rational numbers between 0 and 1, excluding 0 and 1 themselves. We would say that 2, for example, is an upper bound of this set. Now to get even more specific, if we can find an upper bound of A that is less than every other possible upper bound, we have found what's called the least upper bound, or supremum of A. In this case, the supremum of our set would be 1. 1 is certainly greater than every element of our set, and if we tried to go any lower, even by the smallest amount, then it wouldn't be an upper bound anymore. Similarly, we can say that if we can find an element of S that is less than or equal to every element of A, then this element is a lower bound of A. And if it's greater than every other possible lower bound, then it's the greatest lower bound, or infimum of A. So -1 would be a lower bound of our set, but 0 would be the infimum. In this case, both the supremum and the infimum were not actually members of the set. But if our set had instead comprised the rational numbers from 0 to 1 inclusive, then the supremum and infimum would still have been 1 and 0, respectively, but they would have been members of the set, in which case we would have called them the maximum and the minimum of the set. Now, in this example, both our supremum and our infimum were themselves rational numbers. But this doesn't always have to be the case. We could easily have the set of rational numbers x, such that x squared is less than 2. The supremum and infimum of this set would be square root of 2 and negative square root of 2, respectively. But neither of these is rational. But if we were instead to consider the set of real numbers x, such that x squared is less than 2, the supremum would also be a real number. This is true for any set of real numbers. If the set has a supremum, then that supremum must also be a real number. This is called the supremum property of the real numbers. In fact, if a set of real numbers has a supremum, we can actually find it, thanks to Dedekind cuts. All we have to do is take the union of each of the lower sets and find the real number that corresponds with that particular union. That'll be our supremum, right there. The supremum property will come in handy when we start talking about sequences soon. In fact, these properties of the real numbers we've started to discuss are very important to the study of calculus, the branch of mathematics that looks at the effects of small changes in variables and functions, which is absolutely essential to the study of the sciences. We'll be getting more into these properties of the real numbers in the next lecture, when we talk about basic topology. See you next time.